right, guys. So this week we are going to be, continuing from where we stopped out last week. Last week we spent quite a bit of time on descriptive data science. We showed the value of descriptive data science using business intelligence on the tips data set. But from now on, we're going to be focusing on the predictive side. So let's assume that, in our model here for today, we have the housing data, right? So we have some housing data and we want to try to predict the price, the selling price, right? So we're going to assume that there's no analytical models for it. There's no math models or physics models that drive the input to the output. We also can't programmatically define the rules. There's no specific rule that says if these conditions are met, then we know what this price should be. But that might be the case. So suppose the prices were mandated or controlled by the city or by the state, then programmatic models can come in. Right? Or simulation models, this is when there's a lot of randomness. We don't have as much randomness here. So that's why we would go down the machine learning path, right? That is why we would apply machine learning to this problem. Okay, so let's go ahead and jump right into it. And then as we go, we'll start studying this problem. All right, so, the question that we're really trying to answer is, can you build a quick model to predict the sale of prices of houses in Melbourne? So you guys have already seen this data set. Let's go ahead and load the data and see what we find. All right, so the first thing is we're going to initialize like we did last time. This is when we're pulling all of our libraries in. I'm going to be doing a lot of documentation along the way. Hopefully that translates to good documentation behavior on your side as well. So let's bring in pandas, which is our data frame library. And now let's load our data. Okay, let me see if I can, my kernel here, see the reason it's not, didn't run is because there's no kernel here, up here. So let's see why. All right, so this could happen sometimes. And that probably happened because my Jupyter environment, because I shut down my computer some time ago, the Jupyter environment probably reset and it didn't start the kernel. Okay, that's probably why that happened. So if you don't see a number that's being executed, that means there's some issue with the kernel. You can go up here to kernel and then say interrupt, restart, or shut down, right? All right, so now let's go ahead and load the data. And in this case, I have the data, like last time, I have the data in a different folder. By the way, you can also load data from URLs, and we'll do that at some point in time. But here we see that I'm in my notebooks folder. I need to go out to my data folder and then go into housing, and then that's my housing prices folder. Okay, so to do that, I'm going to call my my housing data frame dfmlb, and again, this is naming convention. I usually put a df in front of data frames and then some sort of indicator of what that data frame is. Helps us keep track of all the different data frames we have instead of just calling it df, right? A lot of the code you find out there, it'll just say df. So we did this last time, read csv, and now we're going to go out into the data folder, housing, and then house prices. Okay. All right. Let's take a look at what this looks like. The head function called top 5 rows. So in this, what we're seeing is that, so let's go through one row. So we know what suburb this specific, so every row is for one home sale. The address, the number of rooms, the type, there's I think 3 different types, what price it's sold for. So this is not the asking price, this is what it's sold for. And we're trying to predict what the house sold for. Now, sometimes it might be above the asking, sometimes it might be below the asking. And then you have, who sold it, when it was sold, blah blah blah, right? And then, but if we look at some of the potential indicators, if we put our little prediction hat on for a second, then we know that the number of rooms probably matter quite a bit. Number of bathrooms probably matter quite a bit. The land size, or how big the land area is, and then you have year, and then the location, which is defined by the latitude and longitude. Okay, so we understand what the data looks like. So let's go ahead and maybe let's take a look at all the columns. So if we want to find out what are all the columns in a data set, you see that there's too many columns to view here. That's why you have the little 3-dot icon there. So let's see, pandas, list of columns, right? So you have a data.columns function. If we do df.columns, here we get to see the list of all the columns. Okay, if we need to use that for whenever we are going to use them in terms of setting our data. Okay, all right, so the next step now is we want to select, remember, like we did last time, we want to set our Y and our X, and then start building our model. So here I'm going to assume that we've already done the BI part. Okay, so I've done some business intelligence work already, and I have determined some reasonable columns to pick. Okay, I'm not going to do this in class because it takes time. So here we are now in the select data stage. Now that we've imported the data, all right, and when we're selecting the data, we want to first select, we're going to start using some terminology now. Some of you must be already familiar with it, some of you not. So the first thing that we do when we are selecting the data is we want to select a target. Okay, so we want to select a prediction target, and this is what we are trying to predict. Okay, so this is basically the column that we are trying to predict. So we're, like last time, we're going to call that Y, and we have our data frame. And if you remember, we used the .loc function. I'm going back to last week. We use the .loc function, and we want to select all rows and which columns we want, right? Again, you don't have to use .loc. There's other ways to do this, but I suggest you use .loc because it's the most generic and the what goes across all the examples, right? So we want to predict price. So let's go ahead and do that. Okay, so we've selected our target here, and let's just check to make sure we got that. Okay, so we got price here. Now let's go ahead and choose our features. Okay, and features are what we call our X columns. All right, so let's do that here. And I'm going to be doing a lot of this repetition in every class where we define the target, define the features. In these steps I'm going to go through today, we could do it in a very short manner, and I'm going to do that repetitively so that it becomes sort of muscle memory almost in terms of building these models. So now I want to select my columns, and suppose I've done some BI work already, and I know that I want to go with rooms matter, bathroom matters, which is the number of bathrooms, and then the land size, which is the size of the entire land, not just the building. That building area is covered here, but just go with land size, and then latitude and longitude. Okay, let's just say that we've done our BI, and that's what we figured out as potentially the primary driver. But now we need a model to show how they affect. So let's go with rooms, bathroom, land size, latitude, and longitude. Okay, so we've got our features here. All right, so what we're seeing is there's an error here. Let's try to go and see what the problem is. You see that it's giving an error that says, dot loc is, not, it's something that's no longer supported, or missing labels and things like that. It's thinking that when we pass this in, that some of these columns, might not be in the data set. So you see, it's not telling us exactly what the error is, but it's just saying that some of these columns might not be in the data set. So if we go back and look at our columns, we got rooms, we've got bathroom, land size looks good. Latitude is spelt with 2 T, so some of these might be typos. Longitude is longitude. I mean, we could go back and change the data, but we'll just, change it in our selection and go with it. Okay, so this is just to show that, sometimes when you get an error, it might point in a different direction, but then you kind of have to dig a little deeper to figure out what the real error is. All right, so we've got our X here, and now let's just take a look and see if we're looking at that right. Okay, so we've got rooms, bathroom, land size, latitude, longitude. Okay, so now that we have our features and we have our target, let's go ahead and let's try to see what's the range of values for our rooms and the land size and a number of bathrooms and things like that. So if you remember from last time, we had the describe function, right? So we can take any data frame and then call the describe function just to see what's some basic statistics of each of the columns. So we have, first of all, and it also helps to find out if there's any anomalous data, right? So if there's any missing data. So this is a quick way to do a lot of that. So it's the same number of rows for every column. That means there's no missing data in these columns. The minimum, there's at least one bed, one room, and at most 10 rooms with a mean of 2.9, and so on and so forth. So I guess there's homes with no bathrooms, which is what this means, with a max of 8. And then land size. So this gives some, good indicators of, are there bad data points, or are there some things we might want to take out? For example, we might say, hey, you know what? We don't want to include houses with 0 bathrooms, right? So we probably want to go in and remove some of those data points, and we'll get to that, as we do more and more. Okay. All right. So, but in general, this looks okay. There doesn't seem to be, too many anomalies out there. Sometimes anomalies are, legitimate, like, there's a house with 10 rooms, probably the same house with 8 bathrooms and, a huge size, right? Sometimes we might want to take those out because it's just going to throw our model off. Sometimes we'll say, or it might be an error, or and then sometimes we actually would want to keep it in. All right, so now we are going into the build model stage. Okay, so now that we've loaded our data, we've selected our target and our features. So when we are going to build our model, the steps we are going to take. Okay, so we're going to follow 4 steps, and this is just so that we always remember to do these 4 steps. So the first step is that we are going to define the right model, define the appropriate model. And then the next step is, so let's just say, and then the second step is that we are going to fit the model to the data. And then step number 3 is we're going to predict, other data points using the fitted model. And then finally, we are going to evaluate the prediction, the model's prediction. Okay, so let me just put that in markdown here. All right, so these are the steps we're going to go through, and I call this out because there's lots of times when errors are made because we can combine some of these steps, but then you end up missing certain steps as you're doing this, for many models at the same time. All right, so let's go ahead and do the define step first. So here we are going to define our model, and let's start with a decision tree. Okay, so let's start with the decision tree model, and the question comes up is why decision tree, and let's talk about that for a second. In our model here, this looks very much like a regression model, right? We could just do straight up regression, but let's talk about that for a second. So when it comes to something like a whenever we are building models, decision trees are typically the most basic, the first model you would build. And the reason is that this is how our minds work anyway. See, suppose somebody came and asked us today for the houses that are being sold in Austin, what are the prices like? Or so then we would come up with something in our minds, right? We would say something like, hey, if the number or no, let's say if we are talking about, we say the area is in the northwest part of town, right? If that's a yes, and if the number of bedrooms is greater than or equal to 3, then we might be talking that we can go down and say the number, the area, say the area is greater than, or the square footage is greater than 2,000 square feet. Then we might say that the house is probably in the range of 450 to 500K, right? And then we say, oh no, the square footage is, if it's less than that, if that's the area I'm looking at, and I really want 3 bedrooms, and it's smaller than 2,000 square feet, then I might be looking at something in the 400 to 450K range. And then, so on and so forth. I might say, okay, square footage is, then I might say go down in bathrooms and, blah, blah, blah. So I'm basically in my mind, when I am conveying my estimates of how much home prices are in Austin, I anyway go through something like this. And this is logically how our minds work, right? So that's why decision trees are the most basic types of models that we start with. Okay, so anytime somebody goes and tries to build a more complex model, that's great. But if there was a decision tree that could have made an equally good prediction, then you definitely don't want to have a model that's more complex than that. And one of the main benefits of a decision tree is that it is very explainable. And some of you might have heard about this whole movement out there in data science and AI in more having more and more explainability. Where whenever we build models, we should have very good reasoning why that's happening, and that also helps remove bias, right? So, for example, if we were trying to predict whether somebody should be given a loan or not, right? And then we had a very complex model, not a decision tree, but a complex model that has, it's not very explainable. We won't be able to tell somebody that here's a reason why you're not getting a loan, right? And we may not even know whether there's bias in that model or not. But if we had something like a decision tree, we would say, okay, hey, if your credit score, because your credit score was below some number, or because you haven't been working for so many years, or your credit history is not long enough, blah, 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 that combination is why you're not getting a loan, right? So decision trees are, the most basic types of models, and you really do always want to start with basic models because they are explainable, and you only want to go complex if necessary, right? So that's why we always start with decision trees, and the decision tree here that we are going to go with, because we are trying to predict a number, this would be called decision tree regression. Okay, we could use decision trees to also predict binary values or predict buckets of values. But we'll go into that later. All right. So here we're still talking about regression and predicting numerical continuous values, but we will still try to use a decision tree. Okay. So what happens in when we use a decision tree algorithm? How does it come up with something like this, right? So if you think about it, what's really happening, and this class is not about going into sort of the math behind it, but I still want everybody to understand, how does that happen? Just to understand. So suppose we took just two of our columns, and let's say this is the land size, and this was the number of bedrooms. Okay. Suppose this was just a two feature problem, and we are trying to now predict the home prices. Okay, so this is what these decision tree algorithms are going to do to try to come up with this type of a tree. So first of all, we are going to go and plot. So let's say that you have a bunch of homes in this space, and then you have a few here. So I'm basically plotting the different home prices, okay, with respect to bedroom and land size. And then you have a bunch that's here, and then you have some that's here, okay. And of course, I mean, they're not going to be perfectly divided up. Okay. So now that we want to create a decision tree, what the algorithm does is it tries to find the best way to divide up this region. So it'll say, you know what, I'm going to draw a line this way, and then I'm going to draw a line here to divide up this whole search space, okay? And then I'm going to draw a line here again. I don't need to divide it anymore that way. And then I'm going to draw a line here. Okay, so it's trying to find the best way to split up all these home prices with respect to the number of bedrooms and land size. Okay, so it might say, oh, this is this is 2 bedrooms here, and this is maybe 3 bedrooms, and this is a land size of 2,000 square feet, right? So that's where it's drawn the line, and maybe this is 1,500 square feet that corresponds to this point here. Okay. All right. So, and let's just call this, this is region 1, region 2, region 3, region 4, and region 5. So now, if the algorithm already figured out where to draw the lines, so based on that, this is how it's going to suggest. So first of all, it's going to say, right, is the number of bedrooms less than or equal to 2, right? Which is down here. If that's a yes, then it's going to ask, is the land size less than or equal to 1,500, which is here. That's this first mark here, right? And if that's a yes, then the answer is that sorry, we're talking about 2,000 here, right? Because the 1,500 doesn't matter here. No, so that should be 2,000, right? 2,000. Then we are in region 1. Okay, that means it'll give us the range of prices that corresponds to these homes down here in the bottom left. And then if that's a no, then it's region 2, and so on and so forth, right? So if we say no here, that means we are talking about it's more than 2. Then we say is number of bedrooms less than or equal to 3, which is now that's saying that we are here. And if that's a yes, that means we are in region 3. If that's a no, we still have one more check here that would say, is land size less than or equal to 1500? And if that's a yes, then we are in region 5. If not, we are in region 4. Okay, so you see that this is pretty much what the decision tree algorithm is doing. Okay, it's splitting up the data and then trying to put it in and then puts it into a rule-based kind of tree structure. Okay, hence known as a decision tree. All right, so now how does it come up with these dividers? There are many methods. We're not going to go into this right now, but I will paste a link to a video there's a really good YouTube channel that talks about all these details. Basically, there's a method called the Gini method, which calculates the impurity of each of these buckets. So each of the buckets has, or each of these features has an impurity calculation. Once we want to minimize the impurity. So if you draw a line that improperly splits up the data, it would have a higher impurity. So it tries to minimize that impurity, and that's how it comes up with which features to pick and then how to split them up. Okay? But again, we're not going to go into that here. All right, so now let us go back. So now we know that we would want to build a decision tree model. So let's go ahead and do just that and see what happens. Okay. All right, so we are going to define our model. So let's go to pandas decision tree regression. All right. Like I said last time, we're going to always borrow code instead of trying to learn the syntax. So it looks like decision tree is still within sklearn. We did sklearn last time. It's in a section called tree, and then there is we just call the decision regressor, and then the fit and the predict. So we have all the pieces of code here, so we can start copying that. Right. Okay, so, and if you don't have sklearn, then you're going to have to import sklearn. And now let us define. So this is what we call the definition here. So bring that in. So I like to call my models. I like to put a prefix of MDL for my model so that I know that it's a model object. Decision tree for my Melbourne data set. All right, and it is a decision tree regressor. There are many parameters that can be set. One of the most basic parameters, we can go into. We can go into the details on that later. So we've defined our our model. All right. So the next step that we said would be to fit. And our fit syntax is we just take our model name and then dot fit and x and y. So first our features. Okay, and we define the x and y the same way. X is features and y is lowercase y is target. All right. So it's just built the decision tree regressor right there. You see that random state is none. This is the random seed. So if we're ever going to be doing comparison between models, it's good to set the random state. So let's go ahead and set the random state to any integer or value, right? So I'll just set it to 1 here. All right, then I'm going to call the fit function. And then we said define fit, and then it's predict here, right? So let's sorry, I had by mistake. Okay. We are calling the predict function now. And the syntax for that was dot predict, right? And we are then going to call whatever we want to predict. So in this case, oh, by the way, before we do the prediction, let us look at what this tree looks like. So I'm going to go ahead and write some, plotting code. You don't have to worry about this. This is just for purposes of, visualizing what this tree looks like. So let's just call it show model here. So again, so since this is decision trees, there's ways that you can visualize this. So let's see, there's a way plot tree here. And I'm also going to need matplotlib to be able to visualize this. And then let's see, that figure is what I want. And in a 8x6 frame. DPI 100. And I want to plot the tree of this model that I just created. I want to view only a depth of 2 levels. I want to show the feature names as the columns of X. Size 6, just so it doesn't go over. And to make it look a little bit better, call it filled. All right, and then there's a small tangent here, but I want to show you what this decision tree looks like. All right, so you see that this decision tree model, it created something like what we had drawn out, right? So this is saying if the number of rooms is less than or equal to 3.5 rooms, then we are going down this path. If it's less than 2.5 rooms, down here, if the land size is small, less than 85, then it's going. And since we only said max depth of 2, that's why we don't see any more, right? I mean, this could take a while to render, but anyway. So it's very, very logical, very realistic, very easy to explain this, right? All right, so let's go back and do it now. Make our prediction. So it's the dot predict function. All right, so call it. So let's first. So we're gonna call this as our model dot predict, and we want to predict it for some homes, right? We want to give some x values and predict y. So let's do it for the first few rows. Okay. So this is saying that for the first few rows, remember these first 5 rows, we just made a prediction for what the prices might be based on this model we just created. That's what these prices are. Now let's look at the actual prices for those 5. So the first house is 148 or 1.48 million, 1.03 million. So it seems like all 5 of them are exactly the same. So that means our prediction is exactly on point, right? Now, let's just evaluate that. That's our last step, is evaluate. So let's evaluate and see whether how good is that model. So when we're evaluating, one of the simplest ways to evaluate is, so if we wanted to take the difference between these two, right? So 1.48, the difference between these two, difference between each one of them, and then take the average of the differences. That's one of the most basic ways to evaluate how good a model is. There's better ways, of course, but the simplest way is just take the difference and then take the average of that. So that's called the mean absolute error, right? So that we take the error and then take the absolute of that, so that positive and negative don't cancel each other out, and then take the mean of that. So if we say Python or sklearn mean absolute error under metrics, and it's under metrics, and we just take from a scalar and metrics mean absolute error, then y true and y pred. Okay. Our y true is called y, and our y pred is what we predicted. So let's take this and set it to right. So we have y pred is what we predicted, and let's do it for the whole entire x. I made my y prediction, and then I'm taking the error between what I predicted and what the actual is, right? Okay, so the mean absolute error for predicting between our predictions and our actuals is only $1,100, right? So that means across all the, how many rows did we have? We had across the 13,580 homes, our prediction is, extremely accurate, it seems, right? And, our prediction on average, we're only $1,100 off. Which seems a little too good to be true, right? For something like home prices, which could vary quite a bit. So what we've just done here is and I know, most of us are probably already thinking this, but we just trained our model on our entire data set, and then we are then so our model was trained, right? We fit on all of our rows, and then now we are again predicting all of our rows. So, this model very well predicts everything that's inside of it, but may not do a very good job of predicting what's outside of it, right? And let's see, what difference that makes. But what we've done here, this is actually used sometimes in industry. A lot of people in statistics, I mean, that's all that they have, and so that's what they work with. It's known as an in-sample score. So this is known as an in-sample score, and it tells you how well your model fits the data. But we know that in our case, we are really wanting to predict something that is going to come in future, right? Some new homes that are going to come in the future is what we want to predict. And so, we actually need to take our data set and split it so we want to take all of our rows here, and we want to split some of them. We want to keep some of them away so that we don't look at them right now, as if we don't see them. And then later on, once our model is built, we want to then test our model using those data points. Again, I know that this is probably very common to many of you, but I want to show everybody what is the impact of. So you see that here the error is only 1,100, but if we were to go ahead and split up the data, then and do what we should have done, right? So which is here, split data into training and test set. Okay. If we do that, how much of a difference does it make? So let's first go and grab, let's say, pandas split or data split into training and test. Right here, under sklearn, yeah, there's the model, and it's under model_selection, train test split. Okay, here. So we'll take this. And so hopefully, I know some of this takes a little extra time to go and look for the syntax, but hopefully this shows you what to search for, so that if you had to go do this in some other language, in R or in Scala or Go or any of these up and coming languages, then be able to do that. Okay, so X train, X test, Y train, Y test. By the way, let's try to keep this, uppercase X, upper and lowercase Y, and then underscore training test. It's a good practice to keep it clean. All right, and then X and we're saying that, you know, take my X and Y and split it into these 4 buckets based on a test size of, let's just go with 20% in the test, and it automatically knows that the training is 80%. And let's put our random state, which is our seed, also to be 1. So this now should split our data. And now if we were to go back and say rebuild model, and I recommend that whenever we do this, we, you know, the model building part, you keep typing it over and over so that you get, you know, very good, very quick at it. Okay. So remember, we were doing the define first. So let's call it SPL now because we're splitting. And this was decision tree regressor with random state 1. And then we want to do, so this is define. Then we do fit. So we say model, which is a split fit. And we now want to fit the train, X train with the Y train, right? And then let's do the predict. So we have this model, we're going to do predict, and we are going to try to predict X test. And we are going to call this our prediction of X test. Let's call that Y test pred. Okay, so this is our prediction for the test, and then now we want to evaluate. So let's do mean absolute error between Y test and Y test pred. Okay, so now that we run this, so we've rebuilt the model using the train sets and then predicted only the test and then calculated the absolute error on the test prediction versus the actual. And it's a whopping $238,000, right? So we went from an error of $1,100 to an average error of $238,000, which is, you know, if we take, let's look at the mean home price here. So you got price here. Let's just do, I'd like to see what the mean home price is. So describe, this should give me the price. So the mean home price is about 1.1 million. And so if our error here is 238,000 out of 1.1 million, that's about, you know, almost a 22%, you know, off the mean, right? So so that kind of tells us, right, how good or bad our model is, and of course we have a lot more work to do. So you know, today's in today's, so let's just say that, you know, here we so the in sample model was only $1,100 off, right? Off from the mean on average, whereas the out of sample, which is what we did here, model was $238,000 off from the mean, so which is about 22%. Okay. All right, so this is just for our own notes. Okay, this is what we have learned here. And then what are some of the takeaways? What are some of the takeaways here? One of the things, we've built our first model, all right? So we built our first model. And, you know, we understood, you know, using decision trees, and then we also have learned that it's important to split our data into training and test, right? Now, this is over time gonna seem very obvious to you, um, but it's very important for us to realize what is the value of doing that, and then why would we go with 20%? Should we make it higher or lower? Um, you know, so the smaller that our test size is, we would be fitting our model more and more. So there's a balance between overfitting, which means having a smaller test size. We would be overfitting the model. It would do very well in sample, but poorly for out of sample. Versus, hey, why not go to 60-40, right? Wouldn't that give us something better? But you have to balance between overfitting and underfitting. Okay, so sometimes if you go too low on your or too high on your test size, and basically your training set is too small, then you would be underfitting your model. And in essence, what that does is that your it wouldn't even be able to predict the data points that are within the sample, let alone outside. So there's a point, and we'll talk about this some other time, of how do we find the right spot between underfitting and overfitting. Okay. All right. So with that, I will turn off recording and then we'll continue.